The title of my program, Mars the Great Desert, is somewhat ambiguous. I'm going to pretty much follow on with Wall and discuss what exactly happened to Mars and what the evidence is that it was an electrical event. So we can start by saying that Mars is about 6,793 kilometers in diameter, which is about half that of Earth. Today, its average temperature is minus 63 Celsius compared to Earth at 13 Celsius. And the atmospheric density on Mars is equivalent to standing on top of a mountain 6 times taller than Mount Everest, or 1/800th that of Earth at sea level. Now, on August 12, 2005, NASA launched the Mars Reconnaissance Orbiter on a 2-year mission to map the Martian surface, and since then it's been refunded every year. After several months of flight, it entered orbit on Mars on March 10, 2006. Now, there are several instruments on board the satellite, but the one I'm going to be discussing today in particular is the High-Resolution Imaging Science Experiment camera, otherwise known as HiRISE. HiRISE is a half-meter telescope. In other words, it has a mirror about a half meter in diameter, and it's capable of resolving objects as small as 30 centimeters from 300 kilometers up in orbit. It's from that camera that most of these images are taken. This initial image, of course, is not taken from the Mars Reconnaissance Orbiter. This is an image from the Mars Express, which is a mission that was launched a few years prior by the European Space Agency. Now, Martian areography, as Wall mentioned, tells a story of incredibly violent events. It appears from the many images sent to Earth from HiRISE that it once experienced powerful plasma discharges on a massive scale, and Wall illustrated that by showing the barred spiral galaxy shape on Valles Marineris. As terrain mapping instruments indicate, that's the Mars Orbital Laser Altimeter, or otherwise known as MOLA. The northern latitudes of Mars are 6 kilometers below the mean elevation of the planet. So a great deal of material was removed from the northern hemisphere of Mars and then subsequently redeposited in the southern hemisphere. Burned and blasted craters, piles of scorched dust covering almost an entire hemisphere, and great trenches that wend across its scarred face lead to the conclusion that lightning, thousands or millions of times more powerful than we know today, devastated Mars. Modern science has retained the long hoped for desire that Mars could be the cradle of different life forms and evolving in a different ecology. It's often speculated, as Wall mentioned, that the planet must have gone through a stage where there were oceans of liquid water. There's a lot of disagreement in the scientific community about whether such volumes of water could have ever existed on Mars. Surprisingly, in conventional science, there's disagreement. In the March 5th, 2007 edition of Scientific American, it was reported that most of what has been interpreted as water-based erosion on Mars could have come from, quote, dry avalanches of dirt. The authors expressed serious doubts about whether observations have demonstrated any effects caused by liquid water. Alan Tremaine is one of the major geologists from Houston's Lunar and Planetary Institute, and he wrote, "The idea of it being liquid water was a very reasonable hypothesis to start with, but from my standpoint, liquid water hasn't been proven at all." Now, the large-scale structure of Mars, with its continent-wide canyon, gigantic volcanoes, and monstrous fissures, this is the Tractus Catena region on Mars. I know you probably can't see the scale bar down at the bottom, but this area is approximately 10,000 square kilometers. So that is a very large structure right there. Now, when an electric current passes over a solid body, it can erode material from it or deposit material on its surface where an arc makes contact. The pits or craters left by electric arcs are usually elongated circles because the arcs strike at right angles to the surface while they move. and material in the bottom of a crater or a trench such as Tractus Catena will probably be electrically heated, burned, and melted. If the surface is positively charged, arcs tend to stick in one place, resulting in increased melting, while the electrodynamic forces lift the surface to form what's called a lightning blister or a fulgumite. Fulgumites appear as domes and pedestal craters on Mars, and the largest scale example of a fulgumite is probably the gigantic structure called Olympus Mons on Mars, what's erroneously called the largest volcano in the solar system. If the surface is negatively charged, electric arcs tend to move rapidly after striking and carving out a crater. Small craters on the rims of larger ones are signs of this effect. Sometimes as electric arcs travel, they cut chains of craters, and Tractus Catena, as you can plainly see, is a long chain of craters of varying proximity. The huge canyon at the bottom of the screen is, I don't know if you can see it clearly from where you are, but it has little points at periodic intervals matched by little points on each side of on the other side of the canyon rim. And that indicates that these are elongated circles butting against each other. So actually the Tractus Catena region, representing 10,000 square kilometers, is composed of chains of craters. NASA scientists often refer to what they find on Mars as mysterious or puzzling, with long years of research and contemplation ahead of them. The reason for the confusion is the problem of reverse application. Earth should not be used to explain the solar system. The geological patterns found elsewhere deserve alternative viewpoints. So you can kill the spot. Here's a closer view of Tractus Catena. You can see at the bottom where those points are located. They're right in this area here. And they go along the structure, and along the rim as well in various places. You can see what most of us are referring to as dendritic ridges. Now, dendritic ridges, because these are electrical formations, are most likely fulgurites or scars left by lightning bolts embedded in the walls after the electric arc has removed the material from the bottom. And you can see that the bottoms of this trench, as well as the bottoms of the craters, are scoured clean. There is very little of anything in the bottoms. And on the sides of the crater walls, indeed, there are also fulgurites embedded in them. As I said, Tractus Catena is a huge structure. I think the only other one larger would be Valles Marineris and some of its tributaries like Candor Chasma. Mars has very unusual features as well, and besides Tractus Catena, and some of them are what planetary scientists refer to as dunes. Now, these dunes are unusual in the fact that they don't move. And as we get closer to this structure here, you can see that this particular dune is actually stuck to the side of a ridge. And I don't know how a loosely conglomerated pile of sand is going to stick to the side of a hill. But that's apparently what has happened here. Obviously, the material was melted and blown by an ionic wind, where it then reconsolidated, stuck to the side. And all these vast fields of dunes that you see on Mars, in many cases, have a crust on top of them. And here, one of the things that I'm going to point out that's important is that like Nili Patera, this area where the Opportunity rover was traveling near Victoria Crater, traveled through a field of what they're calling dunes for as far as the eye can see, as you can tell here. These are piles of hematite, which in reality is iron oxide. So, and these white patches that you see in between the hematite, and as you can see here, these patches of white are in reality what they call a pavement of silicon dioxide. So on Mars, in vast areas, are these piles of hematite on top of silicon dioxide. So you have a conductor of iron on top of an insulator, which is silicon dioxide. That's what they form semiconductors on. And as I mentioned, this is near Victoria Crater. Many people have probably seen pictures of that. Now, this is Becquerel Crater on Mars, and this is the floor of Becquerel Crater. One of the interesting things about the craters on Mars is, first of all, most of them are quite large. Becquerel Crater is 100 kilometers in diameter, and it was supposedly created by the impact of an asteroid. But if you look at crater impacts that are caused by asteroids, you do not see this chaos on the bottom of the crater. You see a relatively humpy looking or a scooped out formation. But here you see complex structure. And this is another one of those unusual aspects of Mars. When I first saw this picture, and by the way, these are high-rise camera pictures that are over 700 megabytes in size. So you're able to zoom in and look at images only a couple of meters in diameter. So we're going to go pretty close in this one. I hope your eyes can keep up. So here as we get closer, when I first saw this, I thought these dark bands were layers of dust. And in fact, this is called layering by the planetary scientists due to wind erosion. But as we get closer, we see that these so-called layers are in reality pits that have been eaten into the surface. And these pits form all the layers. These are terraced layers formed by these burned pits. All that dark material is burned and scorched. You see here that there are polygonal structures. There's little points on a lot of these mesas, so-called mesas. And these layers go on and on and on and on, these so-called layers. And what this tells me, and if you'll also notice that the bottoms of these depressions are clean. And if you go even closer, I can't go any closer for you because you would virtually have to cross your eyes to see the things as you get closer and closer. But this whole region here is composed of fractured polygonal blocks. The entire surface is fractured polygonal blocks. Most of them are square. Now this is a photomicrograph. The scale is 10 micron, the scale bar is 10 microns right down there. So this is an extremely small region. And this is the surface of material that has been sputtered. Now sputtering is where you have a substance like aluminum and you want to deposit it on a substance that doesn't normally accept aluminum plating like a piece of plastic. And you put that in a chamber, a vacuum chamber, you apply an electric current to the source material, that converts it to a plasma, and then the plasma deposits on the other charged surface, which is the substrate, plastic or some other material. And as you can see, the surface of the sputtered material looks remarkably like some of the images that Monty showed of his anodes from the Sapphire experiment. There are pits and cracks and other formations that look like ridges and cliffs and craters with arcs with cracks running through them. Now, this is an area on Mars called, what is this area on Mars called? Oh yeah, this was an unnamed area. This is just, this has a number, ESP underscore 02100 underscore 2250. So they don't name this region. But as you can see, the remarkable similarity here between these two formations. One is 100 square kilometers here, and this is 10 microns. But the features are virtually identical. You see the branching, burned scars, the pits, the features that look like cliffs and ridges, and it's virtually indistinguishable. If this were presented to you in black and white side by side with a 10 micron scale bar to that other image, you would be hard pressed to determine which was which. Now, one of the reasons I mentioned the vast fields of hematite and the insulating substrate like silicon dioxide is that I'm going to discuss a phenomenon in science called the Rosenzweig instability. Now, Dr. Ronald Rosenzweig was from MIT, and he conducted many experiments in ferrohydrodynamics. Now, the Rosenzweig instability is, this is a quote from his book, is a prominent example for a surface-driven instability where the deformation of the surface is amplified by an external generalized force, in this case electricity. The normal magnetic field and finally settles at a spatial pattern. So what's happened is, because this conductive material is sitting on a insulating substrate, when exposed to electric currents, it acts like a magnetic fluid because it's ultrafine dust. So it acts like a magnetic fluid, and it's influenced by magnetic fields. And there's his book, Ferrohydrodynamics. Probably looks weird with 3D glasses on. Here's another example of a ferrohydrodynamic pattern. And once again, this is a little bit larger. It's 10 times larger than the other image. This is 100 microns, still smaller than the width of a human hair. So you're looking at Rosenzweig instabilities in a fluidized magnetic substance. In this case, it's iron oxide nanoparticles suspended in a viscous liquid. Now, when the Rosenzweig instability occurs, when a perpendicular magnetic field of whatever strength encounters a conductive medium. Now here, corresponding to this is an area on Mars called Candor Chasma. Candor Chasma is quite large, but it's a mere tributary to the Valles Marineris feature. And as we get closer, you start seeing some very interesting patterns forming here. Look at there's Rosenzweig instabilities in the surface of Mars. They are identical to that ferromagnetic fluid that we just saw. They line up, they travel, they're everywhere on Mars. They're often called spiders in some cases, Martian spiders, and they are an electromagnetic phenomenon. This is due to the fact that the surface of Candor Chasma is covered in the ultrafine hematite that makes up the vast fields of dunes that I showed you that Opportunity Crater or Opportunity Rover is rolling through. And this is Candor Chasma. Yes, Candor Chasma, a Valles Marineris tributary. Now here's another example of the Rosenzweig instability, and this is on a ferrofluid. Now, ferrofluid is, once again, a nanoparticle magnetic fluid with iron oxide in a colloidal suspension. When a perpendicular magnetic field is applied, it forms a lattice, and this is the Rosenzweig instability. It settles into a common pattern, and in this case, they're hexagons. And one of the major things I'm going to discuss is hexagonal formations on Mars due to the Rosenzweig instability acting on the fluidized dust. Because ultrafine dust, if it's conductive, if magnetically conductive, will act like a fluid, and you've probably all seen that by moving a magnet across iron filings. They'll follow the magnet and flow just like a liquid. So here, this is an unnamed crater near Olympus Mons. There are so many craters that it's difficult for them to keep up, I guess, with names. Start naming them Bill and Joe. So Wall had or was it Don, had a slide that Mel and C.J. Ransom had created of an object Mel and C.J. had created, a circular formation blasted into the surface of a substrate with an electric arc. Now you see here are circular formations blasted into a substrate with an electric arc. And you'll notice the texture. Oops, don't want to get too far ahead. You'll notice this texture surrounding the entire region. These are all, once again, blocks, fractured blocks. and they have an odd radial pattern extending out from the crater itself. Now look at this, the entire crater wall, and in fact the region surrounding it. It's as if this crater isn't separate from the surface surrounding it. There's no real demarcation here. It's just you have a flat surface, and then oops, suddenly you have a depression, then another depression, then another depression, and on the wall are hexagons. Now in some cases you might see among the hexagons pentagons or squares. And depending on the strength of the perpendicular magnetic field, a lower strength field will create hexagons, slightly higher will form pentagons, and the highest fields will create squares. This is a region called Seti Mensa. And once again, these formations are referred to as dunes by planetary scientists. However, if you look at them closely, these are not dunes. This is etched into the solid rock. There's no duning here. This is all electrically excavated. And it's highly organized as well. It doesn't look so organized from this scale, although you can start getting hints of it. And as we get closer, you can see that there are definite lines of demarcation between regions. And here at the closest scale, indeed, what do we see here? We see hexagon. And if you could look even closer, you can see that this whole region is composed of hexagonal patterns. They're slightly elongated in some cases. In other cases, they're a little distorted because another hexagon has been, I don't know what the word would be, not blasted into it, but evaporated out. The material is missing. Some of it is gathered into concentrations on the edges of the formations. And that's probably some of the hematite dust that was scoured out of the surface and then subsequently pinched together and left behind after the arcs passed on. But it's really amazing how much of this surface is hexagonal. Now we come to a crater in Schiaparelli Basin. A lot of people have probably seen this one. NASA advertised it quite heavily as proof of the layering, the sedimentary layering on Mars, because these concentric rings are supposed to be where a meteor impact blew out material. How it did it in concentric rings, I'll never know. But the other thing that's odd is this is not a depression here in the middle. This is a mound. And if you look closely, you can see that this has a spiral pattern. And as Dr. Wolf, I believe, talked about, spirals are very prevalent in nature, and electricity creates spirals. Also, once again, you see the dunes, but look here. These are not dunes. These are cuts in the surface. They're not depression or piles of material. These are where material has been definitely excavated away. You can also see the rim of the crater. I use the word crater advisedly. I could say circular formation, but that gets a little awkward. Everyone knows crater. And you see here once again that this is not a depression in the center. These are stacked terraces, once again, just like we saw in Candor Chasma. Here you see a mound of scorched dust that's been obviously cut away somehow, and then the ionic winds blew it off to one or other directions. Closer still, you start saying, oh, look at this. We've got hexagons on these ridges. And you've got these little points too, just like we're in Tractus Catena. So this tells me that this is a chain of hexagonal craters in some sort of circular formation. How this could be created, I have no clue, and I don't think anyone really does, because no one has really experimented with electricity on a planetary scale. I mean, we don't know how electricity behaves at certain scales. Sure, we can demonstrate effects in the laboratory, and I can show you those photomicrographs and compare them to the macro scale. But in reality, we're only guessing when we talk about electricity at these enormous scales. This is the closest image. And it's plain that these are hexagonal formations, and they circle the whole crater. Now here's another example of the Rosenzweig instability. These are, I don't know what the scale is on these, but they're not very big. This is about the size of a petri dish. Now the perpendicular magnetic field, as you can see, has done two things depending on the strength of the field. It's created depressions on this side and mounds on this side. And these mounds have these points in the middle. And you'll often see on Mars, and even in the desert southwest of the United States, you'll see mesa formations that have 45-degree shoulders, and then straight up will be a needle or an angled block, like in Monument Valley, for example. And it's my contention that some of those are probably representative of Rosenzweig instabilities, because Rosenzweig's theory says that you need a fluidized ferromagnetic material, and indeed the desert southwest is composed of iron, largely composed of iron oxides, hematite and magnetite. That's where we mine a lot of iron, and we mine a lot of iron in some other areas, but I won't get into those at this point. Now the reason I showed you this one is this is a region called Gordiae dorsum on Mars, and once again you can see the polygonal patterns as you get closer and closer. This was tentatively identified by planetary scientists as dried mud, like you would see on a plane after a rain and it got saturated. The mud would break up and curl up and form unusual formations. But as we get closer here, you can see that this is no way dried mud. These are not cracks. These are ridges separating these domains that exist side by side with one another. Now this was obviously a very strong electromagnetic field, because the primary formation here is square. And these knife-edged ridges that outline each square are what are often referred to in modern geology as hogbacks. They're ridges that run for long distances and have a knife edge. And they're somewhat mysterious to geologists, because erosion is supposed to be a blurring process, a blurring and a rounding process. Sharp needle forms gradually erode down into blunt dome forms. Steep-sided valleys gradually erode down into wide plains, and sharp river courses gradually erode down into lazy meanders. But in reality, when you look at particularly the Southwest and some mountain ranges, you see that without fail, they are sharp and pointed. Now, if erosion of wind and water is supposed to create blurring, rounding, flattening, and these formations have supposedly been exposed to wind and water for 500 million years, one would expect that they would no longer have sharp needle shapes. However, that doesn't seem to bother anyone. Once again, here's another example of the Rosenzweig instability. And this has created somewhat of a rosette pattern with ridges converging on a central depression. Here's another structure on Mars. This is, let's see, this is in Utopia Planitia, I believe. Or this is Utopia Planitia. And once again, you see that there's this rosette pattern embossed in the surface. And surrounding it are all of these elongated channels. They're supposedly, once again, caused by drying. You know, the surface was once wet and it's all dry. But as you get closer, just ancillary to the rest of the slide, you can see that these are trenches, and in many regards, they are also a chain of craters. If we could get real close to some of these areas, for example here, you would see that this is a chain of craters. And it also has a similar structure to, Gordiae dorsum, these names. Now we're going to get closer still here, and you can see once again, here are the hexagons. They're all over this region. They're also in the background as well, but as I mentioned, it's very difficult to get close enough to see some of these structures without your eyes crossing out of your head. And on the bottom here, you have ripples. This is why I don't know. These are also called dunes. I guess there's just no other thing to call them. And they are actually embossed in the rock. You see here also that the region, if I were to back up a little bit for a longer view, you see the region is relatively clean. There aren't any fields of debris around here. There's no blast debris starting with large boulders and then extending out into smaller and smaller objects. This once again has obviously been cut into the surface. Now you see here too, some of these channels run right through the structure. They're just like this. This is almost like an area where the electric arcs that were carving this region suddenly stuck. Maybe there was an excess positive charge in this region, so the arc stuck briefly and maybe jumped around a few times with the, and you can see here that there's almost a logarithmic spiral effect here. It may have actually then drilled its way in toward the center before extinguishing. I'm actually going a little faster than I thought. Oh, here's the closest image yet, yeah. Here are all the hexagons, and there are some pentagons mixed in here as well. But it's just remarkable to me that what is considerably nothing more than solid rock can be so affected by electric fields and then forming polygonal patterns. And what must have happened is that the material was somewhat vaporized or converted to a dust-like state and then re-solidified after the arc was quenched. And this is another example of the Rosenzweig instability that people may have seen. This is a ferrofluid, and you can see that the cells are hexagonal, and these points come out of each of them. Now this is an area called Utopia Planitia. These regions, this is supposed to be faulting. This is all due to faulting and subsidence and what they call mass wasting, which is the sliding of material down a slope. And this is supposedly what caused all these ridges. But if we get closer here, you start seeing evidence that maybe mass wasting or faulting is not really responsible for this, because you start seeing these areas of scorched dust. And if this was faulting, you would expect that a fault would occur right along here where the area is upraised. But no, these ridges run up and down and up and down, and off to the side down in here is a huge depression filled with this black dust. But the reason I've chosen this image is because we're going to look more closely at some of these so-called fault ridges. I swear, sometimes I think NASA doesn't even look at their own pictures. Because if you look at you go, this is not a fault. Don't they know geology? Here again, fine, okay. Here, I'm almost done. Here again, we see that you've got some of these notches in the ridges. These are not really notchy, but if you get even closer, you see, oh my goodness, these are hexagons. Hexagons and pieces of hexagons. The 120-degree angles are everywhere because, of course, that's what a hexagon is composed of, is 120-degree angles. And in fact, on Mars, 120-degree angles are everywhere. You find them on Earth, too. Everywhere you go, mountain ranges in particular seem to have ridges that meet at 120-degree angles. I happened to overhear two people talking earlier about Shiprock, New Mexico. And indeed, one of the things that when I wrote my article about Shiprock, there is 120-degree lava dikes extending out that are knife-edged and stick out of the ground. They call them lava dikes. Shiprock is supposed to be a pluton that was subsequently eroded. The sedimentary rock was eroded, leaving it exposed to the elements. But once again, it's all pointy. It's not rounded and blurred. And they mention that there are invisible lava dikes too that form hexagons around shiprock. So as we get even closer, you can see that the hexagons become even more prominent. You know, it's almost like a sawtooth. And I think this is as close as we get right here. You can see here's a perfect example right here. These are everywhere. Anywhere you see these long extended ridges, you're going to find these hexagon notches in the top. And this is due to the perpendicular magnetic field accompanying the electric arcs, because electric arcs impinge on a surface at right angles. Oh, we had one more, closer still. It's just further evidence that these are hexagonal formations. Now here's an example of the 120-degree angle formation in a magnetic fluid. This is what they call a Healy-Shaw chamber. It's got electromagnets surrounding it, and this is a ferrofluid being exposed to a 100 kilohertz electric field. So as it evolves, you can see that definitely we're getting 120-degree vertices here, and we're starting to form the semblance of a hexagon. And this is the effect of perpendicular magnetic fields on ferromagnetic substances. And again, here nature prefers spirals. This is the Rosenzweig instability. Another example of the Rosenzweig instability is upcoming. And this one will actually illustrate how the perpendicular magnetic field can take an unconsolidated substance like a geomagnetic powder, ferromagnetic powder. This is 1,000 microns. Now you can see the instabilities beginning to form as the magnetic field strength increases. It's actually pulling the magnetic particles into a hexagonal pattern. And in many cases on Mars, you'll find those sorts of structures. And that's all I have. Sea level. Now on August 12, 2005, NASA launched the Mars Reconnaissance Orbiter on a 2-year mission to map the Martian surface, and since then it's been refunded every year. After several months of flight, it entered orbit on Mars on March 10, 2006. Now there are several instruments on board the satellite, but the one I'm going to be discussing today in particular is the High Resolution Imaging Science Experiment camera, otherwise known as HiRISE. HiRISE is a half-meter telescope. In other words, it has a mirror about a half-meter in diameter. And it's capable of resolving objects as small as 30 centimeters from 300 kilometers up in orbit. It's from that camera that most of these images are taken. This initial image, of course, is not taken from the Mars Reconnaissance Orbiter. This is an image from the Mars Express, which is a mission that was launched a few years prior by the European Space Agency. Now, Martian areography, as Wall mentioned, tells a story of incredibly violent events. It appears from the many Today, the title of my program, Mars the Great Desert, is somewhat ambiguous. I'm going to pretty much follow on with Wall and discuss what exactly happened to Mars and what the evidence is that it was an electrical event. So we can start by saying that Mars is about 6,793 kilometers in diameter, which is about half that of Earth. Today, its average temperature is minus 63 Celsius compared to Earth at 13 Celsius. And the atmospheric density on Mars is equivalent to standing on top of a mountain 6 times taller than Mount Everest, or 1/800th that of Earth. It's a bar down at the bottom, but this area is approximately 10,000 square kilometers. So that is a very large structure right there. Now, when an electric current passes over a solid body, it can erode material from it or deposit material on its surface where an arc makes contact. The pits or craters left by electric arcs are usually elongated circles because the arcs strike at right angles to the surface while they move. And material in the bottom of a crater or a trench such as Tractus Catena will probably be electrically heated, burned, and melted. If the surface is positively charged, arcs tend to stick in one place, resulting in increased melting, while the electrodynamic forces lift the surface to form what's called a lightning blister or a fulgumite. Fulgumites appear as domes and pedestal craters on Mars, and the largest scale example of a fulgumite is probably the gigantic structure called Olympus Mons on Mars, what's erroneously called the largest volcano in the solar system. If the surface is negatively charged, electric arcs tend to all mention that the planet must have gone through a stage where there were oceans of liquid water. There's a lot of disagreement in the scientific community about whether such volumes of water could have ever existed on Mars. Surprisingly, in conventional science, there's disagreement. In the March 5th, 2007 edition of Scientific American, it was reported that most of what has been interpreted as water-based erosion on Mars could have come from, quote, dry avalanches of dirt. The authors expressed serious doubts about whether observations have demonstrated any effects caused by liquid water. Alan Tremaine is one of the major geologists from Houston's Lunar and Planetary Institute, and he wrote, "The idea of it being liquid water was a very reasonable hypothesis to start with, but from my standpoint, liquid water hasn't been proven at all." Now, the large-scale structure of Mars with its continent-wide canyon, gigantic volcanoes, and monstrous fissures, this is the Tractus Catena region on Mars. I know you probably can't see the scale. The images sent to Earth from HiRISE that it once experienced powerful plasma discharges on a massive scale, and Wall illustrated that by showing the barred spiral galaxy shape on Valles Marineris. As terrain mapping instruments indicate, that's the Mars Orbital Laser Altimeter, or otherwise known as MOLA. The northern latitudes of Mars are 6 kilometers below the mean elevation of the planet. So a great deal of material was removed from the northern hemisphere of Mars and then subsequently redeposited in the southern hemisphere. Burned and blasted craters, piles of scorched dust covering almost an entire hemisphere, and great trenches that wend across its scarred face lead to the conclusion that lightning, thousands or millions of times more powerful than we know today, devastated Mars. Modern science has retained the long-hoped desire that Mars could be the cradle of different life forms and evolving in a different ecology. It's often speculated as